So, hello and welcome to the final week of the NPTEL Algebra 2 course. And I'm sorry for the delay, I had some network issues. So, we'll start right away. So, this is week 12. So, just give me a second. Okay, so I'll present my screen now. Okay, so let us um, let us start solving the problems one by one. So first question is saying which of the following groups are simple. Okay, so I do hope that you know what simple groups are. A group is said to be simple if it has no non-trivial normal subgroups other than itself and the trivial group, right? So we need to figure out which of these groups are simple groups. Okay, so yeah, so can Z6 be a simple group? Of course it can't be, right? Because Z6 has a, suppose you take the element, let's say you just take the element, the class of 2 in Z6. Its order is 3. So it will generate a proper subgroup of order 3, right? And it will be normal because Z6 is abelian. So A is not correct, as the subgroup generated by the class of 2 is a proper subgroup, normal proper subgroup. What about option B? Again, option B is not correct, right? As the class of, let's say, anything will work. So let's say the class of 2 only is again a proper normal subgroup of Z8. Yeah, proper non-trivial normal. You should also mention non-trivial, and that's clear. Non-trivial, right? What about option C? Is S3 simple or not? Again, S3C is not correct, correct as we can just take A3. Non-trivial normal subgroup of S3. And what about option D? Is A5 a simple group or not? So option D is correct, right? A5, in fact, AN for all n greater than equal to 5 is simple. Right. Okay, so I missed an option here. Actually, option A was Z5, so I'll just include it in extra. What about Z5? Is Z5 a simple group or not? Of course it is, because it's the order of the group is prime, right? So it cannot have any proper non-trivial not subgroups. Let alone normal subgroups, it can't have any proper non-trivial normal subgroups, right? I mean subgroups. So Z5 is simple as it has no let alone normal subgroups, it doesn't have any it doesn't have any proper non-trivial subgroups as its order is a prime. Okay. So this is all about problem 1, easy. Let's move on to the next question. Okay, so given that A6 is simple, what is the length of a Jordan Holder series for S6? Okay, so your options, okay, so you don't have any options, it's a numeric answer question. So A6 is simple, AN is simple for all n greater than equal to 5. In particular, A6 is simple. We need to find out the length of a Jordan Holder series for S6. So observe that the trivial group, which is a normal subgroup of A6, which is again a normal subgroup of S6, is a Jordan Holder series for S6. Why? Because A6 is simple, so the quotient A6 over the trivial group is simple. Further, A6 has index 2 in S6, it is normal in S6 and it has index 2 in S6. So the quotient group is Z2, which is again a simple group, right? So this is a Jordan Holder series for S6. Hence, length is 2, right? You know that any two Jordan Holder series for a group will have the same length, right? We just picked out a single Jordan Holder series and we observed its length is 2. So length of any Jordan Holder series for S6 will be 2. Okay, let's go to question 3. Every indecomposable module is simple. Okay, so is this true or is this false? Okay, so let's just quickly recall what a simple module means. A module is simple if it has no proper non-trivial submodules, right? And what is an indecomposable module? A module is said to be indecomposable if you cannot write it as a direct sum of two proper submodules, right? Or you can't write it as a direct sum of two non-zero submodules. Okay, if you can write it as a direct sum of two non-zero submodules, then the module is decomposable. Right, so the question is saying whether every indecomposable module is simple or not. So Can you think of, so is this true or is this false? That is the question. So the answer would be that this is false. As an example, take maybe let's say zp square, but p is a prime. First of all, zp square is not simple, right? As zp is it can be embedded into zp square, because mainly because zp square has elements of order p, right? So by Cauchy's theorem, since p divides the order of zp square, there is an element of order p, and hence zp can be embedded into zp square, and is this embedding so zp can be embedded into zp square, and this zp, the image of zp under the monomorphism is a proper non-trivial submodule of zp square, right? So this is okay, it's not simple, there's no doubt about it, but what would be the case? Is it indecomposable or not? So is zp square indecomposable or not? We claim that it is indecomposable. We claim that zp square is indecomposable as a z module. So you assume or suppose that zp square can be written as a direct sum of two submodules, let's say m direct sum m for submodules m and n of zp square. Now why can't this be true? Why can't this be true? So observe that zp square is the cyclic group of order p square, right? Now can you use this fact to show that it can be written as a direct sum? Maybe I'll pause for a minute for you to think. Why is this correct? So m and n are submodules of zp square, right? So in order to show that it's indecomposable, we suppose on the contrary that it's decomposable, and write zp square as m direct sum n for non-zero submodules. Submodules m and n of zp square, right? Now since m and n are both non-zero, what can be the possible cardinality of both m and n? They have to have cardinality equal to p, right? Because if one of them has so the possible cardinalities of any submodule will be, that is a subgroup, will be 0 or p square, right? Now if one of them has order p square, then the other will have to have order 0, right? Which means both have to have order p. So by Lagrange's theorem order of m is equal to order of n is equal to p. So this much we can infer. Now if this is the case, if both of them have order p, then m is isomorphic to zp, right? Because m is a subgroup of zp square. Zp square is cyclic, so m has to be cyclic. M is isomorphic to zp, and in fact you don't even need that, because if the order of a group is p, it has to be cyclic, it has to be zp. Similarly n is zp. Now the direct sum of zp with zp can't be cyclic, right? Thus every element of m direct sum m has order at most p. Why? Because every element of m has order at most p, every element of n has order at most p. So every element of m direct sum n will have order at most p, right? And since it's a z module, the scalar multiplication and the addition are component wise, so every element has order at most p. But there is an element in zp square which has order p square, which is a contradiction. This contradicts the fact that zp square has an element that is a generator of order p square. Hence zp square is indecomposable as a z module. Okay, so let's move on to our next problem. Okay, so next question, this is question number 4, says or asks which of the following are indecomposable as z modules. So your first option is Z12, option B is Z9, option C is Z32, and option D is Z36. So this is very easy. I mean solution. So observe that option A is indecomposable. Yeah, so observe that A is not correct. Z12 will be decomposable. Correct. Z12 is actually isomorphic to, or can be written as Z3 direct sum Z4, right? Option B is not correct again. I mean, option B is correct. We just saw that Zp square for any p is always indecomposable as a Z module. So option B is correct. Z9 which is equal to Z3 square is indecomposable. Or maybe I'll just write it for Zp square. Zp square is always indecomposable, right? For any prime p as seen above. Okay, What about option 3? What about option 3? Hi, Shubhangi, right? Yeah. So, uh, this is the last session, right? Uh, okay, so I'll just give you a. You joined a bit late, so actually I started a bit late. I had some problems with the internet. So, anyways, so let me just give you a brief. Uh, Let me just tell you about what I was doing. So this week probably you have studied about indecomposability and all that, right? Indecomposability of modules. Am I right? Yeah. So I had been solving problems from this week's assignment. So the first problem was to identify which of the following groups are simple. So we had 5 groups. We just needed to identify which of them are simple. Simple means that it has no proper non-trivial normal subgroups, right? So out of this, it's very easy to see that A5 and Z5 are both simple, and none of the others are simple. In fact, any group of prime order will be simple, and for alternating groups, you know that an is simple for all n greater than equal to 5. Question 2 was about finding the length of a composition series for S6. Now A6 is simple, an is simple for all n greater than equal to 5. So a composition series is given like this. This is a composition series for S6, and you observe that the intermediate quotients, that is A6 mod, the trivial group, this is isomorphic to S6, which is simple, and S6 modulo the trivial group is again simple. So this is a composition series or a Jordan-Holder series for S6. By the way, I just need to ask, why is S6 mod S6 simple? Are you there, or am I audible? Yeah, so what I'm asking is, why is S6 modulo S6 simple? I didn't understand. What is length for S for a quotient? I'm just asking S6 modulo A6, is this a simple group or not? Okay, why? What is the order of S6 modulo A6? So S6, you know, is the symmetric group of on 6 letters, and A6 is the group of corresponding subgroup of all even permutations, right? So what is the order of S6 modulo A6? It's just 2, right? So the corresponding quotient will be isomorphic to Z2, which is a simple group, and hence so this is a Jordan series, Holder series for S6, and the length of this series is 2. Okay, so now the next question is about indecomposability. So you know that a module is said to be indecomposable if it cannot be written as a direct sum of 2 non-zero submodules. So the question says that every indecomposable module is simple. You need to identify whether this is true or false. Now the point is that this is false, and the example that I gave is, you just take the cyclic group of order p square. This is a Z module. It's an abelian group, so in particular a Z module, in fact a cyclic Z module. You see that this is certainly not simple because Zp sits inside this, and it is a proper non-trivial submodule of Zp square. Finally, we claim that this Zp square is indecomposable as a Z module. And why is that so? Because if you assume that you can write Zp square as a direct sum of 2 non-zero submodules, m and n, then what are the possible cardinalities of m and n? If m and n are both non-zero, observe that both of them have to have cardinality p, right? Firstly, Lagrange's theorem says that since m is a submodule of zp square, that is a subgroup of zp square, its possible orders are either 0, possible orders are either 1 or p square. Now it can't be 1, right? The order of m can't be the order of m can't be 1, because that would mean that m is 0. It can't be p square, because if it's p square, the order of n will be 1, which would mean that n is 0. But we have assumed both m and n are non-zero, which means that both of their orders have to be equal to p, and thus every element of the Dirac sum will have order p, right? Or at most p, I should say, including the identity element. Why? Because you take any element in the Dirac sum, let's say a comma b, this p times this will be p times a comma p times b, which is 0, right? So every element in the Dirac sum will have order p, but that is a contradiction, right? Because zp square is a cyclic group of order p square, which means it has an element of order p square. Now if it were equal to m Dirac sum n, that would be a contradiction, because in m Dirac sum n, every element has order at most p. So zp square is certainly indecomposable. You can never write it as a sum, as a Dirac sum of two non-zero submodules. Okay. Now what I was currently doing was this problem 4, which asks you to identify which of the following z modules are indecomposable. So the first one is saying, so the first option is Z12, the second one is Z9, the third one is Z32, and the fourth one is Z36. Now Z12, you can write it as a Dirac sum of Z3 and Z4, right? You know this, that Zm Dirac sum Zn is always isomorphic to Z LCM of m comma n, right? This is a very well known identity. I hope you are aware of this, and therefore Z12 can be written as Z3 Dirac sum Z4. So Z12 can be written as a Dirac sum of two non-zero modules, which means that Z12 is certainly not indecomposable, it is decomposable. What about the second option, Z9? Now Z9 is of the form Z3 square, which is of the form Zp square, right? So we know that every Zp square for a prime p is indecomposable, as given in the previous argument, which shows that Z9 is indecomposable as a Z module. Now what about Z32? So Z32, so option C is again correct, right? The idea that we used for to show that Zp square is indecomposable, the same idea you can use to show that Zp to the power n is indecomposable for any prime p and n greater than 1. So it's correct. Zp to the power n is indecomposable for any prime p comma n greater than 1 using the same argument. As the n equal to 2 case. So what you do is you simply write Zp to the power n as a Dirac sum of two submodules m and n, and assume both of the submodules m and n are non-zero. So their possible orders will be either p or p square up to p to the power n minus 1. And if both of their orders are some power of p between p and p to the power n minus 1, then their Dirac sum, if you consider the Dirac sum, every element there will have order at most the maximum of their orders, right? What I mean is, assume m can be written, assume m has order p to the power little m, and assume n has order p to the power k, and where both m and k are greater than equal to 1, less than equal to n minus 1, then m Dirac sum n, if you consider m Dirac sum n, then every element here will have our order at most maximum of m comma k. This you can check easily. and my okay, just a minute, did I say it correctly? Yes, I said it correctly. I don't know why. No, I think I am wrong. um, so why am so my point is, it might not happen that every element of m direct sum n has order maximum of m comma k, or should it? I think this particular statement is not correct, but anyways, the theorem holds still. Zp to the power n is indecomposable, because why is that the case? Because yeah, I think it should be maximum of m comma k. Yeah, anyways, so the point is that z p to the power n you are writing as m direct sum n, and there will be no element in m direct sum n which has order p to the power n, which would give you a contradiction, just as in the case of zp square. And what I'm really worried about is, what would be, can we put an upper bound on the orders of the elements of m direct sum n? So assume that the order of, so take any arbitrary element here, a comma b. Assume that the order of a in m, of course it has to be a prime power. So assume this is to the power a p to the power k1 is identity. This is the order assume, and b p to the power k2 is identity. So can we say, can we put an upper bound on the order of e comma b? So certainly a to the power p to the power m is identity, because the order of capital M is p to the power m, and b to the power p to the power n is again identity. Sorry, p to the power k. So can we say something about the order of a comma b? I think I am just making trivial mistake here. Assume m greater than k. Say this is a to the power p to the power m comma b to the power p to the power m. Now this is identity. B to the power p to the power n should also be identity, right? Because if you take p to the power k, right, of course it will be identity, yeah. So you can take m to be k plus s, then yeah, then b to the power p to the power m can be written as b to the power p to the power k whole to the power p power s. The point is that this is e comma e to the power p to the power s, which is just e, right? So anyways, the order of every element in m direct sum n will be the maximum of m and k, and yeah, that was just a stupid confusion. So yeah, the order would be maximum of m comma k, and since m and k are both less than n, so their maximum will be less than n, which is a contradiction, because we have assumed that zp to the power n can be written as m direct sum n. So there should be some element in m direct sum n having order p to the power n, but we just saw that every element has order at less than p to the power n, right? So yeah, so so zp to the power n is again indecomposable for any prime p. So z32, which is z2 to the power 5, is indecomposable. And what about option D? Is z36 decomposable or indecomposable? So z36 is decomposable. Whenever you have at least two distinct prime factors in n, Zn will become decomposable. So z36 is decomposable as z36 can be written as z4 direct sum z9, right? So option D is again incorrect. So which of these are indecomposable? Z9 and Z32. So is it clear, Shubhangi? Is it clear? Or do you have a question you can ask me? Okay. Please feel free to stop me if you have a question. So let's move on to the next problem. Okay, so question, what is this? Question 5. So which of the following are possible dimensions of an indecomposable Q module as a Q vector space? So option A is 0, option B is 1, option C is infinity. Okay, so you need to find out which of the following are possible dimensions of an indecomposable Q module considered as a Q vector space, right? So observe something interesting about vector spaces. You know that every vector space has a basis, right? So what happens if a vector space over a field has dimension more than 2? More than 1. If that is the case, then observe that you have a basis with n elements, or you have possibly infinitely many elements as well. But the point is, once you have a basis with more than one elements, you can split that basis into two parts, into two non-empty sets. One set contains a single element and the other set contains elements, right? And the point is that you can just take the span of the single element and you can take the span of the rest of the basis elements. You get two different non-zero subspaces. So the only possibility here is option B. So since it's indecomposable, we always assume that any indecomposable module is non-zero, right? So we can't, so the dimension can't be 0. If the dimension is 0, that means the basis is empty, then you just get the 0 vector space. But since we are talking about indecomposability, we'll discard option A. This is just a convention or something. Now what about option B? Okay, so I'll just instead of saying which of these are correct, I'll just I'll just write down the argument. Since so let V be an indecomposable Q module since V is not equal to 0, hence option A is not correct. Now suppose V has dimension greater than 1. Okay, so I'll just even before that, why are one dimensional vector spaces indecomposable? So if dimension of V is equal to 1, then V has no proper non-trivial subspaces or submodules. Thus V is in particular indecomposable. So a simple module is always indecomposable, right? That's obvious. So if V has dimension 1, it's simple, which means that it will be indecomposable. Now suppose that the dimension of V is strictly greater than 1. Take a basis B of V over F or over Q. By the way, there is nothing special about Q here. You can just work over an arbitrary field. So take a basis B contained in V over Q. Take a basis of V. Now since dimension of V is strictly greater than 1, coordinate of B is strictly greater than 1. Consider any element V belonging to B and consider the sets or consider the subspaces the subspace generated by V and the subspace generated by B minus singleton V. Since B is a basis, you can see this easily. So then B is a basis implies basis of V over F over Q implies that V is equal to the subspace generated by V direct sum the subspace generated by B minus singleton V, which shows that V will be decomposable. V is decomposable. Hence, option C is incorrect. So thus option B is correct. If the dimension is 1, it's indecomposable, and none of the other options are correct. So option B is correct on me. Yeah. Okay. So let's move on to the next problem. So question 8. What is the number now? Question 6. So let V be a finite dimensional vector space and T from V to V be a linear map. Which of the following is equivalent to saying V is equal to kernel of T direct sum the image of T? So option A is the kernel of T should coincide with the kernel of T composed with T, and option B says that the image of T should be equal to the image of T composed with T. So this is just a computational problem. So which of these two options will be correct? So what do you think, Shubhangi? Is option A correct? Sorry, I couldn't hear you. Is option A correct? Okay, no. So let's try to see if it is correct or not. So suppose kernel of t is equal to kernel of t composed with t, then so what you need to show is v, whether v is equal to kernel of t direct some image of t or not, right? So first of all, can we claim from this, if the kernel of t is kernel of t square, can we say that kernel of t intersection image of t is 0? So let v belong to, you want to say something? V is equal to tw for some w in v, because v is in the image of t. Thus t of v is equal to t square of w, right? And v is in the kernel as well, so thus v belongs to kernel. T implies 0, which is tv, is also equal to t square w, which implies w is in the kernel of t square, that is t composed with t, but this is again equal to the kernel of t as we have assumed, which means that tw is equal to 0, but t of w is just v, so v is equal to 0. Hence kernel of t intersection with image of t is equal to, is trivial. So this so we are one step close to showing that that v can be written as a direction of the kernel of t and the image of t. The rest that we need to show is v, every element of v can be written as a sum of an element of kernel of t and an element of image of t. So let v belong to v, then you can write, sorry, oops. Yeah, then you can write v is equal to v minus tv plus tv, right? You can write this. Now tv is an element in the image of t, there's no doubt about it. If we can show that v minus tv is in the kernel of t, we are done. Now this, so this belongs to image of t, so we want to show that v minus tv is in the kernel of t. Now is this correct? Is v minus tv in the kernel of t? So v minus tv is tv minus t square v. I mean t applied on v minus tv is tv minus t square v. Yeah, but that doesn't imply that. Does it imply this? No, I think. If we would have t is equal to t square, we would be done, right? But that's not the case here. Okay, let me think. Okay, if the kernel of t is kernel of t square, can we not say something more? So certainly, by the way, Shubhangi, which of these two inclusions are correct? Is kernel of t always contained in kernel of t square, or is the opposite inclusion always correct? Now, which one of them is correct? Is in general, is kernel of t contained in kernel of t square, or kernel of t square contained in kernel of t? Okay, why is that? Assume v is in the kernel of t square. That means t square of v is equal to 0. That means t of tv is 0, which means that tv is in the kernel of t. But that doesn't mean v is in the kernel of t, right? So the inclusion that is always correct is this one. If v is in the kernel of t, then tv is 0, which means t square of v is also 0, right? So what this is saying extra is that this what assuming the equality says that this is correct. Kernel of t square is contained in the kernel of t. This much we know. Now this is what I am concerned about. So the kernel of t square is kernel of t. What can we say from this? Whatever t square annihilates, t also annihilates that. But does t square annihilate v minus tv? I don't think so. If tv is we need to get a decomposition for v in terms of an element of kernel and an element of image. That is what we want to show, right? So what is the right way to show this? This is what I am confused about. Okay, let me get back to this in a few minutes. For the time being, I'll just I'll just leave some space for this one. So let's talk about the next question. So question so which of the following rings are local? Okay, option A is Z12, option B is Z9, option C is rationals such that rationals A over B such that 7 doesn't divide B, and option D is Z12X. Okay, so do you know what a local ring is, Shubhangi? Are you aware of what a local ring is? I am audible, right? Hello. Yeah, do you know what a local ring is? If you don't know, you can just say I don't know, and that's okay. So local ring is precisely a ring which has a unique maximal ideal, that is, which has exactly one maximal ideal. Okay, so and local rings, I mean, it's just there's a reason for naming them local. That reason comes from algebraic geometry. So in commutative algebra, there is a process called localization of a ring, in which what you do is you take a ring, you take a some specific subset of the ring, and what you want to do is you want to obtain a ring in which there are inverses for every element of that subset. That is, you want to introduce inverses for every element of that chosen subset. This is called a localization procedure. Okay, so by the way, I didn't sort of get to know you properly. What is your current level? I mean, are you doing a BSc, MSc, or what? You are currently doing? Uh, Maybe you can unmute yourself, or if you are having an issue, you can just write down in the chat. Please interact, otherwise, it's very difficult. Okay, fine. So what I was saying is this localization procedure is sort of, I mean, doing some localization algebraically means concentrating on some specific point, around some specific point geometrically. Roughly, what this is what it means. And local rings have, I mean, they are called local rings for a specific reason. That's sort of the geometric reason behind it. But anyways, let's not get in digress so much. uh, you just need to identify which of these rings are local, that is, which of them have unique maximal ideals, or exactly one maximal ideal. So does Z12 have exactly one maximal ideal, or it has more than one maximal ideals? Can you give me an example of a maximal ideal of Z12 first of all? See, unless you speak up, this is very difficult for me. So A is not correct, as the ideal generated by 3, the class of 3, this is what I mean. Ideal generated by the class of 3 and ideal generated by the class of 4 are distinct maximal ideals. Of Z12. So ideal generated by the class of 3. What is that ideal? So you just take the class of 3 and you multiply with it. You just take the class of 3, you multiply it with all elements of Z12, right? So you have 0, you have 3, you have 6, which is 2, and what else do you have? Threes are 9, right? And yeah, you have 9 and 0 and 15, which is 3. Yeah, so it repeats after that, and this is a maximal ideal. Similarly, ideal generated by class of 4 is again a maximal ideal. and I mean, what I mean by this is there are no ideals sitting above that. Proper ideals sitting above the ideal joined by 3, and there are no proper ideals sitting above the ideal joined by 4. Because any ideal which sits above the ideal generated by 3 will contain 4, and if an ideal contains both 4 and 3, it will contain 1, the difference, and hence it will contain the whole of the ring. It will be the entire ring, right? So certainly ideal generated by 3 and ideal generated by 4 are distinct maximal ideals. What about option B? It's Z9, and option B is correct, as the ideal generated by the class of 3 is the unique maximal ideal of Z9. Why is it maximal? Because if you take Z9 and if you take the quotient of Z9 by the ideal generated by the class of 3, you get Z3, which is a field, right? So so this is the only maximal ideal of Z9. There are no other ideals other than this. Okay, so okay, maybe I am a bit wrong about part E. I don't think the ideal generated by class of 4 will be a maximal ideal. Why is that? Because the class of 2 times the class of 2 is in this, but class of 2 is not in this. So this is not a maximal ideal. Something else has to be maximal here. I think the class of why is Z12 not a local ring? Ideal generated by class of 4. Yeah, that's clearly not maximal. Yeah, ideal generated by class of 3 and ideal generated by class of 2, right? I'm sorry for this. Yeah, these two will be distinct maximal ideals. Yeah, not 4. Yeah. Okay, so option A is correct, option B is correct, option A is not correct, option B is correct, option C is correct. What is C? Consists of all rationals such that 7 doesn't divide the denominator of the rational, right? So this is precisely as this ring is isomorphic to the local ring Z localized at the prime ideal generated by 7. So I'll just write it down. Z localized at the prime ideal 7 generated by 7. Now what is this exactly? What you do is you take the complement of the prime ideal 7 in Z. This is your set S, and you look at all fractions of the form A over S, where A is in Z and S is in capital S, that is outside the prime ideal generated by 7. So it's of the form A over B where 7 doesn't divide B, right? And this can be turned into a ring. Of course you need to identify two fractions. If two fractions cancel to give you the same fraction, you identify them. I'm putting everything under quotes, it's not very precise, but yeah, so this set can be turned into a ring. The usual way you add and multiply fractions, these are your operations, and this ring will be a local ring. The only unique maximal ideal of this ring will be the elements of the form A by B, where A is a multiple of 7 and B is not a multiple of 7. Okay, why is that the case? Because everything outside this has been turned into a unit, right? So this is precisely the set of all non-units. This A by B, where A is divisible by 7 and 7 doesn't divide B. This is precisely the set of all non-units, which will be a maximal ideal. So the unique maximal ideal of Z localized at 7 is A over B, such that 7 doesn't divide A, and sorry, I should mention it properly, A over B in Q, such that 7 divides A and 7 doesn't divide B. You can check that this will be the only maximal ideal. And what about option D? Z12x. Okay, so D is again incorrect. As Z12x is as Z12x is not local. Why is that the case? You can just take, so the point is that so what is essentially Z12x? It's the ring of polynomials over Z12 in the indeterminate x, right? So why is this not a local ring? Because you can just take you just need to find two maximal ideals in this, right? And so what possible maximal ideals can you have? So let's say you can just take the ideal generated by 6x minus 1 or something. Maybe you can just take the ideal generated by 6x okay, so yeah, you can just take okay, let me just write it down properly, it's not correct. So you can just take the ideal generated by 2 comma x, and you can take the ideal generated by 3 comma x. These are both maximal ideals. Okay, let me just check one thing. Yeah, are both maximal ideals of Z12x as Z12x modded out by the ideal generated by 2 comma x is isomorphic to. So the order of 2 here is what is the order of 2? The order of 2 here is 6, right? So this is isomorphic to Z12 modded out by this, which is isomorphic to, so this is 6, this is 12, this is isomorphic to the field Z2, and Z12x modded out by the ideal generated by this is isomorphic to Z12 modded out by the ideal generated by this, which is isomorphic to Z3, which is again a field, right? So yeah, that's it. So option A is not correct, option D is not correct, only options B and C are correct. Okay, so let us move on to the next problem. Let M be equal to Z2 direct sum Z3, considered as a Z module. What is the size of end Zm? So what is end Zm? You just look at the Z module M. You just look at Z linear maps from M to M. These are all the endomorphisms of the object M in the category of Z modules. So this is what your NZM. Now you need to find what is the size of this. So it will be a monoid. What is the size of this monoid? In particular, it will be a set. So we can just say it will. What is the size of this set? So yeah. So your options are A is 2, option B says 3, option C says 5, and option D says 6. Okay, so solution, M, which is Z2 direct sum Z3, is actually isomorphic to Z6. Thus endomorphisms over Z of the object M is in bijection with endomorphisms of the object Z6, of the Z module Z6. Now Z6 is cyclic. Z6 is a cyclic Z module, as you already know, and arrows Z6 to Z6, I mean Z linear, I should say Z linear maps from Z6 to Z6. Z linear maps of Z6 into Z6, or Z linear maps from Z6 to Z6 are given by their action on the class of 1, which is a generator here, right? So one thing to keep in mind is that, so what you essentially want is, any map from Z6 to Z6 gives you a unique map from Z to Z6, and conversely a unique map subject to the property that it sends one to some element of order 6 in Z6, right? Should I say element of order 6, or yeah, I mean the maximum order is 6 only. And conversely, any map from Z to Z6 is completely given by its action on 1, and if the map sends 1 onto some element whose order is I mean 1 onto some element such that 6 times that element is 0, then again you are getting a map from Z6 to Z6. Okay, So let me just write everything in detail. So observe that Z linear maps from Z6 into Z6. So this is in bijection with Z linear maps from Z into Z6 such that what happens, such that this map factors through Z6, which means that 6Z should be in the kernel of the map, which means that 6 should be mapped onto 0. So such that 6Z is contained in the kernel. Okay, and what does that mean? That means 1 is mapped onto an element A in Z6 such that 6 times A is 0. Now any map from Z to Z6 is given completely, is completely determined by its action on 1, as Z is a free Z module, right? Also, no matter wherever 1 is mapped onto, 6 times 1 is 0. So also every map from Z to Z6 contains 6Z in its kernel. Since number of maps, I mean every linear map, yeah, I should mention this, every Z linear map. Since number of Z linear morphisms, that is maps or arrows, from Z to Z linear morphisms from Z to Z6 is 6, precisely because Z6 has 6 many elements. Hence cardinality of endomorphisms over Z, I mean Z linear endomorphisms of Z6, which is equal to 6, which implies cardinality of NZM is equal to 6. So 6 is your correct answer. Okay, let us move on to the next problem. Just see. Okay, so this was question 8. So question 9. How many indecomposable submodules does the Z module Z mod 100Z contain? So this is a numeric types problem. So solution is, so you have to find out the number of indecomposable submodules of Z mod 100Z. Firstly, what are all the submodules of Z mod 100Z? So the submodules of Z mod 100Z are in one-to-one correspondence with the submodules, order preserving one-to-one correspondence with the submodules of Z which contain 100 of Z, right? 100 times Z. So what are those containing 100 Z? So let's just so the canonical map from Z into, so the canonical map from Z into Z mod 100Z induces a bijection, an order preserving bijection of the set of all submodules of Z mod 100Z so bijection of this set onto, so bijection of this set into which we can say onto because it's a surjection, onto the set of all submodules of Z containing 100Z. Now the submodules of Z containing 100Z are Z, 2Z. So whatever is the prime factorization of 100Z, right? So Z, 2Z, 4Z. So 100 is 10 times 10, which is 2 square times 5 square, right? So 10Z and so 2, 4, 10. Okay, so 5 I forgot. 5Z, 10Z, and what else? What else is there? So 25Z, 50Z, and 100Z, right? And therefore we know that one, so 1, 2, 3, 4, 5, 6, 7, 8, right? So I hope I'm correct here. Yes. So there are exactly 8 many submodules of Z mod 100Z as well. We need to find out which of these submodules are indecomposable, right? There's the submodules of Z mod 100Z are Z mod, you just take the quotient by 100Z. So these are Z mod 100Z, 2Z mod 100Z, 4Z mod 100Z, 5Z mod 100Z, right? 10Z mod 100Z, 25Z mod 100Z, 50Z mod 100Z, and 100Z mod 100Z. Now certainly this 100Z modulo 100Z is trivial, we don't need to worry about it because indecomposable modules are non-zero. Now what about the rest? Z mod 100Z is certainly not indecomposable because you can write Z mod 100Z as Z mod you can write it as 4Z mod 100Z, direct sum 5z 25z mod 100z, right? You can write it like this. Yes, you can. Yes, you can write this. So this is certainly not indecomposable. This is decomposable. Is 2z mod 100z decomposable? So what is the order of 2z mod 100z? It's 50 essentially. Now so again, since it's 50 order, it's precisely your cyclic group of order 50, and this is again decomposable. So this is just your Z100. This is decomposable. This is isomorphic to Z50, which is again decomposable. This is isomorphic to Z25, which we know is indecomposable. This is isomorphic to so this is isomorphic to Z20, which we again know is decomposable. This is isomorphic to Z10. I hope I am doing it correctly. T, yeah. So Z100, and you look at the class of 4. Side Z100, you look at the class of 4. It has order 25 years. Class of 5 in Z100. So it has order 20. Yeah. So this is again decomposable. Whenever this Zn has more than one prime factors, I mean it has at least 2 distinct prime factors, then it becomes decomposable. That's the idea. This is Z4, which is indecomposable, and this is Z2, which is indecomposable, and this is just 0, which is by definition decomposable, because we want indecomposable modules to be non-zero, right? So Z4, Z2, Z25, I think I missed one of them. Z4, Z2, where is Z5? I forgot to write 20. 20Z. Yeah. So 20Z mod 100Z. This is isomorphic to Z4. Oops, sorry. This is isomorphic to Z5, which is again indecomposable. So 1, 2, 3, and you have 4. So correct answer is 4. So correct answer is 4. There are 4 such submodules, right? And yeah, so that's all from my side. So if you have any questions, you can always email me. I always write my email ID at the beginning. You can always email me And since no one is here, so I'll stop this session, and I wish you all the best for your exam. So yeah, so see you.